The Sun has always appeared to humans as a flat disk, although we've long known it as a sphere. Now, a landmark NASA mission called STEREO invites the world to actually see the Sun in 3 dimensions. To help us better understand our closest star and how it impacts life on Earth. This mission, featuring 2 nearly identical spacecraft on opposite sides of the Earth, has provided a truly revolutionary view. For the first time in history, the STEREO twins have dramatically revealed the 3D structure of massive solar storms, some hurtling towards Earth. These large solar eruptions, called coronal mass ejections, contain up to 10 billion tons of mass and can travel the entire length of the solar system, ripping through space at mind-boggling speeds. When a big solar blast hits Earth, it can scramble satellite operations, zap city power grids, and even harm unprotected astronauts in space. Will one of these intense solar blasts impact our planet? Much like we predict the weather on Earth, space weather forecasters want to better predict the weather in outer space to provide more accurate alerts when a big storm is headed our way. Join these solar explorers on their 3D mission, where we track the most powerful storms in our solar system coming from our life-giving star called the Sun. The twin STEREO spacecraft are now in the Sun's orbit, and a 5 billion-year-old star is ready for its close-up. The Sun is 93 million miles away from Earth. But by using STEREO, lead NASA scientist Dr. Madhulika Guhathakurta will soon be closer to the Sun than anyone ever before.
It goes back to the Lewis and Clark days, essentially. It's just moving from one frontier to the next.
With the help of STEREO, the exact arrival time of a solar storm can be predicted within 2 hours, 12 times more precise than in the past. Space weather expert Bill Murtaugh helps warn the public of the Sun's most destructive blows.
In space weather forecasting, the STEREO mission is going to give us an insight much like the Doppler radar did for weather here on Earth. When we see the eruptions in the Sun, we call it a coronal mass ejection, a CME. We'll be able to have a side view of them for the first time to see how they expand. We're going to be able to watch the CME as it travels the 93 million miles from the Sun to Earth.
Coronal mass ejections are the most violent explosions in the entire solar system. A gigantic shockwave filled with electrically charged gas. It travels through space at more than 1 million miles per hour, at least 400 times faster than a speeding bullet. The sheer power is equal to millions of volcanic eruptions exploding at the same time. A flood of high-energy particles can break through the Earth's protective bubble called the magnetosphere, charging up our atmosphere and the very ground we walk on. Record-breaking solar storms have caused a citywide blackout in Quebec, sent space station astronauts scrambling for cover, and most recently, disrupted communications with GPS satellites for a very tense 10-minute period.
We are in an era where we have introduced this concept of space weather because it matters to us now. We are studying the sun and earth as a coupled system, not individually, and that new science is called heliophysics.
It will be revolutionary. In any case, when you see more, you suddenly have insights you never had before. Up until now, our situation has been like trying to diagnose the ocean with one buoy.
Stereo is a 2-spacecraft mission, and both spacecraft will be in orbit around the sun, but not in the same place. They're going to be separating from each other, and that'll give us 2 eyes on the sun. We're going to be seeing the sun in 3D.
With the stereo spacecraft, we're going to improve space weather prediction by a factor of 2.
The stereo spacecraft are very complicated. There's a suite of 16 instruments on each one. Together, they analyze the flow of energy and matter from the sun to the earth. Everyone wears full clean room suits to guarantee the instruments are kept as pristine as possible so they'll operate in orbit.
When we have launches, what we don't think about is that there are so many things you have to do right to make it work. And all it takes is a small little thing to make it go wrong. Yes, you are as if praying, holding on to your breath. The launch was just marvelous. It was a spectacular October sky. And it was a night launch. Go stereo! It was just beautiful. You could see the trail forever.
The 2 stereo spacecraft are launched together and then separate. The solar panels are then released. They come out in 2 waves. Once this operation is complete, the sun provides electricity for the twin observatories, enabling them to learn more about the sun's power. Once a day, an antenna transmits the data to the science team back on Earth. A complex series of signals are received at NASA Mission Control to ensure all 16 instruments are deployed correctly. When a solar flare erupts, 3 20-foot-long antennae measure radio wave spikes that provide important clues to the true 3-dimensional structure of these eruptions. From that point, they slowly open up all of the other instruments. The twin stereo spacecraft were then ramped up to their full power, and the team was ready to go. Mission Control is at the Johns Hopkins Applied Physics Lab in Maryland. The crew is divided into 2 teams, one for Stereo A, the other for Stereo B. The twin stereo craft were launched together and then separated, one placed ahead of the Earth, the other one behind. They look at the sun simultaneously, giving the stereo team the world's first three-dimensional images of the sun and solar storms. At the heart of the stereo mission are instruments that trace the invisible high-energy particles streaming from the sun. Space between the Earth and sun is not empty. It's filled with the sun's super-hot atmosphere streaming out into the entire solar system. This stream of energetic particles is sometimes smooth, other times turbulent. It's called the solar wind. A coronal mass ejection is a massive storm of energized particles that rips through this solar wind. It interacts with the Earth's magnetic field in disruptive ways.
We're extremely interested in what happens on the sun because we live in the atmosphere of the sun. So if the sun sneezes, the Earth will catch a cold. Fortunately, we have the magnetosphere that acts almost like a Kleenex and keeps out most of the nasty radiation. If you had a bird's eye view, it would look a little bit like a magnetic squid.
The sun's most energetic particles can disrupt Earth's magnetic field. Electrons storm into the Earth's atmosphere in the polar regions. This creates the northern and southern lights, the aurorae.
When you see the aurora, I think everyone who sees them for the first time is just blown away by how beautiful they are. They really do look like shimmering curtains of light flowing in the breeze.
Using a special radio receiver, we can convert the signature of solar particles zooming through the Earth's magnetic field into sound. The dancing lights of the aurora can be mesmerizing in the cold night sky. But they're also a reminder that solar storms affect life on Earth in many ways.
NOAA, the National Oceanic and Atmospheric Administration, is responsible for space weather forecasting at the Space Environment Center in Boulder, Colorado. We monitor space weather 24 hours a day. We have that responsibility to warn the public when something's happening in the sun that might affect us right here on Earth. We're watching big sunspots in the sun, measuring their size and their complexity.
The sun's turbulent storms ebb and flow roughly on an 11-year cycle. At the high point of the cycle, or solar maximum, there are many more sunspots and storms in the solar atmosphere. This is also when coronal mass ejections most often occur. Warnings that a large solar event is in progress are issued when an eruption is spotted on the sun. These huge explosions impact radio and GPS systems here on Earth.
Space weather for the next 24 hours is expected to be severe. Geomagnetic storms reaching the G4 level, solar radiation storms reaching the S2 level, and radio blackouts reaching the R3 level are expected.
On the 6th of December in 2006, a volatile sunspot cluster appeared in the sun, resulting in a powerful eruption. This actually produced the largest solar radio burst we've ever observed.
We didn't expect there to be a large solar radio burst during the quietest part of the solar cycle.
It just came out of nowhere. It was 10 times bigger than we had seen before, ever. This incredible surprise.
We were counting the number of GPS satellites that were on track, and normally every 30 seconds you're seeing 10 satellites, 10 satellites. All of a sudden it goes down to like 2, 1. I mean, it's like there was this huge effect.
Pretty much every GPS receiver in the hemisphere was affected. Many of them just failed outright, ceased to navigate.
It only happened on the sunlit side of the planet, but it was instantaneous and it was global.
Unlike a CME, this solar radio burst is traveling at the speed of light, so it reaches Earth in 8 minutes. And this solar eruption resulted in flights being rerouted away from polar routes, This extraordinary radio burst itself affected air traffic controllers across North America. So now we had to just drop everything and rethink this situation. What is the biggest we could possibly get? We just, of course, don't know.
As a society, we've become increasingly reliant on technology. Few people today leave home without their cell phone. Many of us have GPS receivers in our cars. We rarely, if ever, consider the possibility of not having electricity when we return home. We have power grids that are sensitive to the electric current that's caused by these supercharged particles from the sun. Blackouts can cause multi-million-dollar devastation and even loss of human life. Satellite operators recognize that space weather can have a significant impact on their spacecraft, so they point their satellites in a safer direction to protect them from high-energy particles coming from the sun. In order to better support human exploration of the sun and Mars, we must find ways to protect the passengers and spacecraft from the harmful radiation that streams from the sun, especially the fierce outbursts during these violent eruptions. To understand and to be able to accurately predict when these high-energy particles might be coming towards Earth is critical to our future in space.
I can't imagine any other missions that are more directly relevant to humankind. By studying the sun, we are understanding this object that influences our life in every conceivable way. But to view that in 3D, I really can't quite envision myself. I get emotional if I think about it.
These are the very first three-dimensional images from the stereo mission in their full glory and detail. This cauldron of magnetic soup, spitting out loops, jets, spikes, churning constantly. The science team uses colored filters that reveal the different parts of the sun at different temperatures. The dark regions are called coronal holes. That's where the solar wind blows out. What you also see are these beautiful rays called polar plumes that seem to extend forever. When you see these coronal loops, they come from the hottest parts of the sun. This is where coronal mass ejections can erupt. Because of stereo, scientists will finally understand the true 3D shape of all these structures. They will be able to better predict how much energy is stored inside these loops. This will help solve some key mysteries of the sun.
What touched me the most is this young kid with glasses on, pointing his finger and saying, I can as if touch it. That's the first reaction of the 3D sun for the rest of the world. It's just jumping out at you. I've always been fascinated by the night sky, by the stars, the galaxies. What is there beyond? To probe deeper and deeper and deeper into a given object. So I think it's humankind's destiny to move out and beyond, to understand.